Welcome back. This is Dr. Kofelt again, and we are doing the final part of the atoms, molecules, and ions. In this part, we named the ionic compounds in the last section. Now we're going to move on and we're going to talk about the molecules, or the covalent molecules, as opposed to ionic compounds. So we're going to differentiate between them, and then we're going to also do empirical formula at the end of this section. So a molecule is a combination of at least two atoms in a specific arrangement held together by what we call electrostatic or covalent chemical bonds. These electrostatic forces are pretty strong, and they occur between nonmetals. Remember, ionic was between metals and nonmetals. The molecular or covalent bonds are just two nonmetals. Hydrogen molecule is called a diatomic molecule because it contains two atoms that are the same thing. Other elements also can occur normally as diatomic molecules: nitrogen, oxygen, and then fluorine, chlorine, bromine, and iodine gas. In homonuclear diatomic molecules, both atoms are the same element. So like in the case of H2, okay, a diatomic molecule can contain atoms that are different. So they are heteronuclear diatomic. So you could have carbon monoxide, for example. So a chemical formula denotes the composition of a substance. A molecular formula is the exact number of atoms that each element has. An allotrope is one of two or more forms of the element. Two allotropes, like for example in carbon, you can have graphite like you have in lead pencils. You can have diamonds, which are very different looking, or coal even, are all forms, allotropic forms of carbon. And they have very, very different properties because it just depends on how those things are put together. A structural formula shows not only what molecules they are in shape, but it also shows us the general way that they are put together. Okay, so we try to put some type of structure with those. Molecular formula just shows us the ratios of the different atoms, but structural shows us that they're hooked together in a certain way. So based on this ball and stick model, structural formula of the ethanol, let's write the molecular formula, okay? So the two black ones are carbons, so we got C2, the H's are the white ones, okay? And then this one is an O. Notice that this O and this H are together. That's your OH molecule. So you could write this C2, and then ever how many H's there are. 1, 2, 3, 4, 5, 6. H6O, or since we know it's an alcohol, you could write it C2H5OH. So you can have different molecular formulas as well. So when naming molecular compounds, we're going to keep it simple with binary molecular compounds, two different elements. And first we're going to name the element that is the cation, like we saw before. And then the second one is going to be ide, okay? So let's look at these we did with ionic. With these, binary, what we're going to have to do is tell the person how many there are of each thing, because they can be in different proportions. What am I talking about? Oh my gosh, I'm talking Greek. Huh. We use Greek prefixes to denote the number of atoms of each element present. The exception to that is if it is only one of the first one, then we don't have to say mono. But if there's only one of the second, then we have to use the mono prefix. So here are those prefixes I told you that you need to make sure that you know. Okay? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And those are 1 through 10 for your numbers. And you use those same ones for your hydrates. So in this naming system, we have carbon monoxide. Notice that we do, instead of saying monoxide, we just drop one of the O's because it's easier to say. And then carbon dioxide, because it has 2. Sulfur dioxide, when you have more than one of the first one, you're going to say dinitrogen, but you still just use the nitrogen name. And then penta or pentoxide, saying that we have 5 oxygens. So as I said, we omit the mono if it's the first element. Sometimes we will drop the A or the extra O when we name an oxide to make it just a little bit easier to say. Some things have just recognized names. For example, the common name is the recognized name for H2O is water instead of dihydrogen oxide. And then NH3 is known as ammonia. Okay? And then the ammonium ion is NH4+, the polyatomic. So name the following binary molecular compounds. So we have NF, so we only have one nitrogen, but it's the first one, so we don't have to say mono. And then we have 3 fluorides, so trifluoride. The second one, N2O4, is dinitrogen tetroxide. Notice that I dropped the A from tetra because it's just easier to say and to write. All right, so there it is, pretty. And then writing the formulas also, you've got sulfur tetrafluoride, and then tetraphosphorus, so P4, decasulfide, S10. I like these. I think they're easier. Anyway. So there you are, some to practice, as well as there are some that you can practice with in some of the extra practice worksheets and things like that. So the last thing we're going to look at are acids. And simple acids, they follow a pretty simple rule. You can have an H, and that's how you'll know it's an acid, because it'll have like an H at the beginning. And a lot of binary compounds are acids. So for example, hydrochloric acid, hydrofluoric acid, and there's a table in your textbook that shows you how to name these different ones. The oxo acids are going to have polyatomics in them. And so they would have, if they were from a polyatomic, for example, NO3, if I add an H to that to make it an acid, then that's going to be nitric acid. If I have SO4, 2 minus, and so I have to add 2 H's to that one so that it has the +2 there, that's going to be sulfuric. So instead of sulfate, sulfuric acid. So look up and see if you can do the names for these. If it is the sulfate, it's going to be sulfuric. If it's the ite version, remember it was sulfate or sulfite. If it has one less oxygen, it's going to be sulfurous acid. So one less oxygen will be the OUS, the sulfurous. Okay? So since molecules can have multiple formulas, they can have what we call an empirical formula, is the fourth type of formula. The empirical formula is the lowest whole number ratio. Okay? Now, remember in ionic, we don't have like H2, like, no, that's not a good one. Let's say Na2Cl2. If we had that, then we would have to reduce that to NaCl. But in the case of molecules where we have the two nonmetals, you can have multiple combinations of these. What do I mean? Okay, so in the case of water, water is H2O, and the one is understood, so we've got 2 hydrogens and 1 oxygen. So the molecular formula and the empirical formula, that is the lowest whole number ratio, is the same. In hydrogen peroxide, though, we have H2O2, so the empirical formula for that would be HO, because you could divide both of those into it. HO is not the same as H2O2. So when you have the molecular formulas, they're going to be completely different compounds, but you can have an empirical formula that could be multiple things. For example, acetylene, which is C2H2, has an empirical formula of CH because you can divide both of those by 2. Benzene is C6H6. Both of those you can divide by 6, and so the empirical formula for acetylene and benzene is the same, CH, because they're in the same ratio, the same proportion to each other. So that's just for the empirical formula, okay? So write the empirical formula for these molecules. So glucose, which is C6H12O6, we can divide those by 6. And so the empirical formula for glucose would be CH2O. Adenine has got C5H5N5, so we could divide those all by 5 and get CHN as the empirical formula, lowest whole number ratio. N2O, though, we can't divide anything because that's a 1 and that's a 2, so its empirical formula is the same as its molecular formula, N2O. All right, so again, you should have some to practice with these in some of your worksheets.